game. Okay, this is one of those problems where the most intuitive thing isn't actually the valid approach. And the most intuitive thing is actually more difficult to technically develop the code for than the non-intuitive simple solution. So this is one of those problems that throws you through a loop. This is one of those problems where the interview gives it to you and they almost expect you're going to conclude the most intuitive thing and they're going to smile like, this fool has fallen for my trick, because this problem will trick you, okay? But we'll get right into it. So you're given a 0-index 2D array grid of size 2 by n. Okay, that's kind of strange, right? Because usually grids are m by n. So this 2 by n thing first should set off a little alarm about what the nature of the solution is going to look like, right? So it's 2 by n, all right? Which means that, we have 2 dimensions here and n dimensions here, right? So it's 2 and then n. So n is the variable. It's not m by n, it's 2 by n. So this little 2 thing, so strange, you should think about that. Where grid RC represents the number of points at position RC on the matrix, okay? So, each of these things, there's going to be values associated with them, X, Y, Z, A, B, C, whatever, right? So there's values associated with each of these grid cells. So there's values on them, and I guess that means something. Okay, now you have 2 robots that are playing the game on this matrix. Okay, both robots initially start at position 0. Okay, so there's 2 robots here at position 0. And each robot may only want to move to the right, may only move to the right or down. Okay, so it can only go right, can only go down. All right, so at any position when there's a robot, right, it can either go right or it can go down. All right, it can't go left, it can't go up. At the start of the game, the first robot moves from 0, 0 to 1, n minus 1. So they start here and they end here at the edge, right? Whatever that bottom edge is, right? So they go from one edge to the other, going right and going down. Okay, collecting points from the cells on its path. For each cell that it traverses, the value of that will be set to 0. Okay, so if this initial robot, goes down this path, for example, which is valid, right? Because it's only going right and it's only going down. That's going to result in all these cells being zeroed out. So all these values will become 0 across the path that it took. So what does that imply for the second robot? Well, when the second robot goes right, he's not going to collect any points on these paths because they've all been set to 0, right? This used to be X, Y, Z, A, B. Now it's 0, 0, 0, 0, 0. Okay. Then the second robot moves from 0, 0 to 1, n minus 1, collecting the points on its path. Note their paths may intersect one another, right? So this first robot is going to go through and collect all these points, and the second robot will go through. It can traverse the same path. It can go a different path. It doesn't really matter what path it takes. Just understand that now that it's traversed this new path where there's been modifications, it's not going to be able to collect all the same points, right? Because this first robot went through and collected it all himself first. Okay. The first robot wants to minimize the number of points collected by the second robot. In contrast, the second robot wants to maximize the number of points it collects. If both robots play optimally, return the number of points collected by the second robot. Okay, so this first robot's going in and he's just being a jerk. He doesn't even care about his points, really. He just cares about minimizing what the second robot's going to get, right? So the first robot comes in, he's just scheming, and he's thinking, you know what I want to do? I want to minimize the number of points that the second robot can get. So what path can I take to minimize what that robot gets? And the second robot, when he goes in, he's going to say, okay, the first robot, he just removed a bunch of points. He really tried to make things hard for me, but I'm going to use what's left and try to maximize the number of points that I can get, okay? So with that said, let's go ahead and get into this first example. All right. So in this example, we have 2, 5, 4, 1, 5, 1. Now you can see that this first robot optimally will take this path. Okay. So that means that the system then turns into 0, 0, 4, 1, 0, 1. Now the second robot, what is going to be his optimal path now? Well, he could go down and then to the right. That would give him 2, or he could go right, down, right, 1, or he could go right, right, down, 4, 1, 5. So he could get 5 points by taking this path. All right, simple enough. Wait. Oh, sorry. This one is covered. So 2, 5, 5, and 1 all turn to 0. Apologize. All right, everything that you traverse turns to 0, including the last cell. So this person would get 4 points. All right, simple enough. And I'm having glitches, aren't I? And this is another example. So this would be the path. This would be the path the other person would take. Here's another one, right? So this is the path you take, and this is the path you take. Now, why is this problem hard? So, like I was saying in the beginning, there's something about the intuitive thing being wrong. What is the most intuitive thing in this case? Well, if I'm trying to minimize the next person's score, then that would mean that I should take as much as I possibly can for myself. Right? That seems the most intuitive, at least to me, right? It's like, if I'm the first robot and I want to minimize what the second person will do, and they start at the same spot I do, and they're trying to get to the same spot, and they have the same restrictions about what they can do, well then, if I want to minimize his score, I should maximize my score, and that'll result in his score being minimized, right? And, it seems that way, right? Like, there are counterexamples, and I don't even know the formal proof, like, to logically tell you that that's not the case. Because even to me, now that I thought about the answer and thought about the terms of how to think about it, I've seen counterexamples. I don't know the logic behind why that doesn't work, right? Because it's like, I'm trying to minimize your score, number 2. I'm number 1, I'm trying to minimize number 2, so then I'll just maximize number 1, and then your number 2 is minimized. But that's not necessarily the case, right? It is not always the case that maximizing number 1 score will minimize number 2 score. Right? Kind of, because what number 1's trying to do is not maximize the score, he's just trying to screw it up. Right? He's trying to make it as hard as possible for number 2 to get points. So making it as hard as possible for number 2 to get points might not necessarily be, what maximizes your score. And I guess the best way to think about that as well, if you get, let's say you get, Now, I'm trying to think of an example here on the fly to try to make, because now that I'm thinking about it, I'm actually starting to think about what might actually be the case here. Okay. So say 1, 1, 1, 5. Doesn't really matter. 10 here. 1 here. 4, 1, 1, 1. Oh, I can't think of an example, but what I'm trying to say is basically like, this might be the optimal path here. Right, 6, 7, 8, 9, 10, 20. But this would have to exceed that. I don't know. Basically, there are examples. I apologize, guys. I'm starting to get to the general idea, but I can't think of a counterexample. But the idea is basically, I want to cut off all the paths that this person can take. Okay? And the best way to make this work in your mind is to think about what the implications of the path would be, okay? And since this is a by 2 system, there's kind of clear implications about what would happen based on what the second robot would do. If that doesn't make sense, I will explain right now, okay? So let's look at a general example, right? And let's think about the scores that that the second robot could get based on the first robot's actions. Okay. If the first robot, and then we're just gonna call these things all, I don't know, A. We'll just call them constants. C1, C2, C3, C4, C11, C21, C12, C13, C14, C15, C16, C17. I made this way too big for no reason. All right. This is a bad video today. C21, C22, C23, C24, C25, C26, C27. I don't know why that was so hard. Okay. If the first robot takes any path, let's think about what the implications are in terms of what the second robot could get. Okay. So let's imagine that the first robot took this path. All right. If the first robot took that path, what are the scores that the second robot could get? Well, these things would all be cleared out. Right? Ugh. Gosh darn it. Right? So these would all be 0. So what does that mean in terms of what the second robot could get? Well, what you'll notice is when I split it like this, there's only 2 things that the second robot can get. Because the robot can only go right and it can only go down. So if the robot goes down, it could get this. What are the 2 maximum things it can get? Of course, it could do this and get nothing, right? But it's going to behave maximally. Or it could do, this and get less. But the second you go down, you can't go back up. So you might as well go down as quick as possible. Right? So it can either get this maximally or it can get this maximally. Right? So if the first robot takes this path, the second robot will take the max of C21, C22 plus C22. Or it'll take C14 plus C15 plus C16 plus C17. Right? What about another path? Let's just keep doing this so we can try to develop a pattern here. And then we'll see how this is easily implemented optimally. What if instead he took, I don't know, this path? Or, I don't know, this path? Well, we get a different resulting system here. But you'll notice that the pattern here is the same. Right? The optimality for C2 in this situation, yet again, is, well, let's erase all these. Well, what can this second robot do? Well, it can either take C21 or it can take all these up top. So it could take it's going to take the max in this situation, C21 or C13 plus C14 plus C15 plus C16 plus C17. Okay? Because that would be what the optimal thing, right? So always optimally, it's either going to go straight down or go all the way right and over, right? No matter what, no matter where I put this thing. I'll do even one more, right? If I take, like I can look at each individual path that this person could take. Let's look at the first path. What if red took this path? Well, then in this case, right, still going through, right? All these would be deleted. So, he could either, the second robot could either take pretty much peep squeak nothing going down or everything to the right. So you could take the max of nothing or all the stuff to the right. C12 plus C13 plus C14 plus C15 plus C16 plus C17. Right? So then what does that mean? Well, see robot 1, right? Robot 1 can decide which path it's going to take based on this logic, knowing what robot 2 is going to try to do. Because robot 2 is trying to maximize this path, and it's very simple in terms of what robot 2 can do based on what robot 1 does, right? If robot 1 does this, then robot 2 has these 2 options. If robot 1 does this, robot 2 has these 2 options. So really what I'm thinking about is the point of which I turn. And since the system is only based on, it's only a by 2 system, right? The second I go down, I can only go right. So really, there's only one down move you can make, right? So I can only make one down move. Both robots can only make one down move, right? So really, I just need to say, where is the optimal place to make a down move? Do I make the down move here? Well, if I make the down move here, these are the implications. It could take either this or this. If I make the down move here, well, here's are the implications. You can either take this or this. If I make the down move here, here are the implications. You can either take this or nothing, right? So all I need to do is look at each down move and say, for this down move, what would he do? Okay, for this down move, what would he do? For this down move, what would he do? And I'll take the min of that, right? So I'll look at each down moves. For robot 1. And I'll say, okay, what will robot 2 do? I called it R1 and then robot 2. Let's keep it consistent. What will robot 2 do? And I'm going to take... What will robot 2 do? Robot 2 will do the max of its two cases, right? Its two cases being either it goes straight down, either goes straight down and to the right, or goes all the way right and down. And I'll figure out which one is the minimum. Results in the minimum situation. And that's pretty much it. Okay, so how this will work formally so we can ensure that we're running in an efficient timeline is I'll keep track of what I think is the minimum run. Okay, so here's how it's going to work. I'll keep track of what I think will result in the best thing for me, so I'll call that result. Okay, and I'll set that to infinity first, right, just to have it set to something. That's going to be my initial value. And then I'll look, okay, if the robot 2 goes all the way to the right, what will their score be? So that'll be the right score. And what if they go down and then all the way to the right first? That'll be their down score. Okay, so how does this work functionally? Well, let's think about this. So for the first run, if I went down on the first run, corresponding to this, what scores could robot 2 get? Well, he could get 0 going down, or he could get C12 plus C13 plus C14 plus C15 plus C16 plus C17 going right. Okay, because that's the initial situation here. I'm trying to find what the initial situation is so then we can kind of reverse engineer it a little bit, right? To say, okay, how do we build this efficiently? Because what we don't want to do is calculate these things every single time, right? We don't want to calculate what all these values result in every single time we go through. We want to have that information catch somehow so we can kind of remove it and deal with it as it comes up. Okay? So in this first situation, we'd have going down, we'd have nothing, right? Because that would result in this all cleared out, right? Everything red cleared out. And going right, you would get C12, C13, C14, C15, C16, C17. Okay, so that would be the sum of this whole thing minus this first value, right? That's what you would get going right for the second robot. So let's create a variable S, which is the sum of the first row. Okay, so this is the sum of the first row, S, and we'll subtract out C11, and that'll be this value here. Okay, and we'll subtract that from the sum. I don't know how to represent that here, right? Because basically R in this first case we'll put down above R because I want to represent R as a sum of things. So R in the first case would be, what would the robot 2 get if it went right? It would get C11 plus C12 plus C13 plus C14 plus C15 plus C16 plus C17. But then since robot 1 starts in this spot, this one goes away. So this actually isn't a part of it. Okay, what about the next run? Now that I have a kind of a basic idea about how this is going to work. Down, okay, situation 2. If I went down like this, what could robot 2 get? Well, robot 2 could get C2 going down, or it could get C13, C14, C15, C16, C17, plus. Right? And it's the same game over and over again, right? So now, what if I went right here? Well, it couldn't get C13 anymore going right, but it could get C14, C15, C16, C17. And then what about going down? Well, now it could actually get C21 plus C22. Right, so these things are kind of building the sums as you go, right? And what res is going to be is, well, whatever the minimum of what res could be using a previous down, and what res could be if the person went down or right, or they're maximizing these two. So you just go through this. So if we keep this whole sum, and as we go through, like when we're on this down one, we remove C1 from the sum. When we're on this down one, we remove C2 from the sum. We're on this down one, we remove C1, 3 from the sum. So we calculate the sum once and then subtract out each down point as we go. And we start with down as 0 and we add in each down point as we go because we know that if we're going down here, well then now it has these two available for robot 2. Okay, so that's everything I'm going to do with that. Very terribly written. Let's get this... Hey! All right, let's get a thumbnail. All right. So let's go ahead and write the solution for this. Okay. So like I said, we want to keep a sum of the first row. And then we're going to look at each down move. We're going to have what we get if we went down, which starts at 0, and then what we get going right is actually this sum, t, and we'll just subtract from it as we go. Now we'll look at each spot of which we could actually make the down for the first robot. And we'll say, okay, if I make a down here, well, if I'm going down here at this point, they're not going to get this point going right? Like, if I make a down here, this next person doesn't get 5. Right? I make the down here so they don't get the 5. So I'm going to remove that from my sum because at each down point I'm going forward, right? So I've already subtracted the 2. So if I subtract the 2, look at what the down is. I subtract that from t. Now when the next down point where I go down, I remove the 5. So then that means that 2 has already been removed, right? So I say t equals t minus grid at 0 at I. And I look at what this person would do. So I need to figure out what my result is going to be. So I'll start as float infinity, and I'll return it at the end. And I'll say, okay, maybe a previous down point gave me the minimum, so I'm going to keep track of my previous down point. Or this person, robot 2, this robot 2 could do two things. Robot 2 could take the down path, or they could take the right path. Or they go right and down, or they can go down initially and then go right. Okay? Now that I'm going right, well, if I go down here, it doesn't get anything, right? But the second I move forward, I skip the point before, so that point is now included in what you get going down. So now down would be down equals down plus grid 1 of I. So initially we thought this problem was like trying to find the maximum path, right? So you're going to do some sort of like either dynamic programming, what's that called? Warshall algorithm, or you would do like uniform cost search Dijkstra's algorithm or something. But it's really simpler than that, right? Like this thing is a beautiful runtime. And what is the runtime? Okay, so let's say n is the length of. Look at that, guys. Talk too quick. Why is that wrong? Oh, well, you never get, well, that doesn't matter because you never add that in. Wait. T equals T minus grid 0i. D equals D plus grid 1i. The very beginning. Why is this wrong? Let's see. Talk too quick, man. All right, so in this example, it's saying 16 is the optimal it could get. But no, what if I turned here? So let's print out everything here. Res, T, and D. Something here I'm messing up. It's probably very obvious, and I apologize for that, guys. Very embarrassing. Oh. Res. Re's like a pattern matching library or something. It's been a while. So the second one would choose 19 in the first path. Oh, because length of grid 0. Oopsies. Right, because grid is just 2. Grid 0 is the actual width, right? That's the number of down points that I could go going right. How foolish of me. Okay. What is the... But that's a good lesson in debugging, right? Okay, so what's the time and space complexity? So let's say n is the length of grid 0. We don't need length of grid because it's really just 2n. 2n is always just big O of n. Okay, for time, well, we sum grid 0. So we have to look at all n elements in grid 0, sum it up. And then we look at all down points in grid 0. So we look at all n elements again, all n down points. We do a constant operation, constant operation, constant operation. So we do n operations and another n constant operations. Return sum, just big O of n. For space, well, we sum up grid. We set that to a constant variable regardless of the size. Set it res. We set it. Notice we just create these 3 variables and we update them accordingly. Okay, so that's big O of 1. All right, guys, peace out.